Unit 2. It's a very wordy unit. فيها رغي كتير with definitions و descriptions كتير. So you kind of need to understand what we're talking about. بس في نفس الوقت there's a decent amount of, unfortunately, rote memorization. Very few calculations, especially to those in year 9. Let's take a look at what we'll talk about today. We're going to first talk about the differences between solids and liquids and gases, the general things. إيه اللي بيحصل when things change state and when you heat them up, and definition of temperature and such. We'll talk about evaporation and the difference between evaporation and boiling, and we'll also talk about thermal expansion. Now, all of these are just different effects caused by heat. Following that, we're going to talk about gases by talking about Brownian motion. It's a very simple experiment. We're going to review what happens when a gas applies pressure and what affects the pressure of a gas, which we call the gas laws. We'll then move on to conduction, convection, radiation, which are the methods by which heat is transferred. And finally, we're going to talk about thermometers. That's for year 9. However, starting this last section over here, this is not for year 9, this is for year 10s and 11s. So as soon as I hit that point, I'll call this out again and let you know if year 9 students want to leave. But we're going to finish up the chapter by talking about 2 equations which we use to calculate heat energy. Okay, so remember, if you see this particular, sign, no, it's not for pre-IG. Okay. Let's get started right away. We'll start by talking about the differences between solids and liquids and gases. And before I discuss this, because you've probably seen this again in chemistry and you're pretty bored of it, but before I discuss this, it's very important to notice that in physics and in thermal physics, we're going to sometimes talk about an object or a substance from the outside, which is its shape, its volume, its temperature, its pressure, quantities that we can measure من برا. And then we're going to talk about the substance on the inside. And there are 3 things we will always talk about: how the molecules are arranged and how close or far they are, how the molecules move, and how strong the bonds are between them, because all molecules have forces between them. So first, let's get started. Solids have a fixed shape and a fixed volume on the outside. We say liquids have no fixed shape and no fixed volume. They take the shape of the container they're placed in, whereas gases have no shape and no volume. They fill up the container they're in. This means that if you have a room, for example, a nice big room, and I tell you what's the volume of the gas in the room, it's the volume of the room. It fills up the entire room. Okay, next, in terms of molecules, we say that solids molecules are closely packed. This means 2 things. One, the space between molecules in a solid is very small, and there's almost no spacing, and they are regularly arranged. There's a particular order to the molecules. The molecules, however, do move and they do vibrate about a fixed position. So the molecules don't move around and they don't slide, they just keep vibrating in a fixed position. And finally, all of this is because they have extremely strong bonds. The forces between the molecules and each other are very, very, very strong, which keeps them, closely packed and vibrating about a fixed position. Liquids are loosely packed, which means they still have relatively small spaces. The spaces are still small between the molecules. However, there is no arrangement. It's all completely messed up and it's random and things are, not very ordered. The molecules do move by sliding over each other, so they still can't move freely, but the molecules can change places with each other as they see fit. And finally, the bonds are still strong. In solids, they're very strong. In liquids, they're just strong. I know sometimes in chemistry we just say weak, but it's preferable in physics to say strong bonds because we want to differentiate between these 2. Finally, for gases, as you can see, all of the molecules are far apart. There's no order, there's no arrangement, there's nothing. They move freely, fast, randomly, high speeds, do whatever you want. And that's all because they have extremely weak bonds between the molecules, very weak bonds between the molecules. So that's all said and done. One very important thing to note is this. Since we said that solids and liquids and gases, all the molecules inside are moving, so molecules are moving. This means that all of the molecules inside a specific substance have a certain amount of a type of energy, which is called kinetic energy. Kinetic energy is the energy of movement. So the faster the molecules move, the more kinetic energy they have. And it makes sense to say that gases have more kinetic energy than liquids and more than solids and so on. Next. We want to talk about a couple of things, temperature and internal energy. There are just a couple of definitions that we're going to be referring to, not very frequently, but we're going to be referring to occasionally. First, what is temperature? Temperature is how hot or cold something is, but it's actually defined as the average kinetic energy of the molecules in a substance. This means that, as we said before, the molecules are all moving and they're vibrating, or they're sliding over each other, or they're moving freely, if it's solid or liquid or gas. But when you heat something up and you start to give it a lot of heat energy, the molecules start to move faster and faster and faster. That's on the inside. On the outside, you feel the temperature rising. It's getting hotter. It's harder to touch. But on the inside, the molecules don't know what temperature means. It just moves. So the molecules are either moving slowly or quickly. فلما التمبerature بتزيد بنقول kinetic energy of the molecules increases, and if the temperature decreases, the kinetic energy decreases as well. The only reason we say average, or one of the reasons we say average kinetic energy, is because it's not fair to assume that every single molecule has exactly the same amount of energy. Like, they don't really have perfectly the same amount of energy. Some molecules have lots of energy, some molecules have less energy. What you feel when you touch an object or you measure its temperature is the average. Next, internal energy. The word internal means on the inside, اللي جوه. And there are two types of energy inside a substance. Kinetic energy, which we've already agreed exists because the molecules are busy moving and such. And potential energy. Potential energy is the energy stored inside, the molecules when they're far apart from each other. The further apart the molecules move, the more potential energy they have. And this is going to be important because when we heat any object, sure, its temperature rises, but in a bit we're going to talk about volume, and we also say its volume increases. That's called thermal expansion. And for the volume to increase, the space between the molecules has to increase. And to increase the space between the molecules, we have to increase another form of energy inside it, which is called potential energy. Okay, next one. This definition of internal energy does not show up very frequently when it comes to questions, but temperature is extremely important, very important. Okay, excellent. Before I move on, just a quick look at the chat. Okay. Moving on. Good, we have about 70 people in here. Next up, let's talk about how substances change state, and it's quite simple. If you have a solid and you start to heat it, eventually it'll change to a liquid, and that process is called melting. If you have a liquid and you heat it, eventually it'll change into a gas because it goes through the process of boiling. I did not say evaporation, not yet, just wait. If you have a gas and you cool it, it'll change back to a liquid, and that's called condensation. And if a liquid is cooled, eventually it'll change back to a solid, and that's called freezing. Here's the thing, remember, when you want to heat a substance, you need to give it heat, meaning you need to give it heat. So melting and boiling occur. And when something is condensing or freezing, it's losing heat. So you could say it's being cooled in both of these cases. Second point to mention is that during melting and during freezing, they don't happen at any moment in time just because you're heating or cooling. They only happen at a specific temperature called the melting point of a substance. So for example, ice melts at 0 degrees Celsius. This means that if you have a piece of ice at -5 degrees, for example, and you're busy giving it heat, it's not going to melt yet. It's just going to heat up until it starts to melt at 0. Water, for example, boils at 100 degrees Celsius. We call this the boiling point of the liquid. So that's that as well. when a gas, let's say you have some steam at 110 degrees Celsius and you decide to cool it, it's not going to condense until it reaches 100. So the boiling point and condensation point are the same. Melting and freezing are the same. The only difference is that if you're giving it heat, it's melting. If you're taking the heat away, it's freezing. But another very important point is this. If I plot a graph of how the temperature of a substance changes over time, and please note احنا العلامة دي اللي أنا حاططها مش كاتب T لسبب. Sometimes هتشوفوا في paper 6 when we solve this next week. Sometimes instead of writing T or temperature, he uses this symbol which we call theta. This symbol has been used in math before. I'm pretty sure you've seen it when they talk about angles and such. But this symbol is often used for things measured in degrees. So in this case, degrees Celsius temperature. المهم, when you have a solid substance like ice, let's say I've got some ice over here at negative 10 degrees Celsius, and you heat it up, the temperature is going to rise and rise and rise until it reaches 0, which is the melting point of the ice. But while it's melting, the temperature stays constant. This means that the kinetic energy is not increasing. The kinetic energy is not increasing. Instead, during melting, the energy absorbed by the molecules, the heat energy that we're giving it, is used to, during melting, is used to weaken the bonds between the molecules. Because when you want to change a solid to a liquid, let me just go back for a second. When you want to change a solid to a liquid, you kind of want to increase the space between the molecules a bit, and you want to make the bonds a bit weaker to do that. So the energy during melting is used to weaken the bonds, just to make the bonds a bit weaker. Same thing goes when it comes to boiling. If you heat a liquid up, it'll just heat up normally, no problem, until it reaches the boiling point. Remember, this is water we're talking about here. During boiling, the temperature stays constant. It does not increase, it does not decrease. And that's because the energy is used to, as you can see, break the bonds between the molecules. You want to move the molecules so far apart that the bonds break and it changes from a liquid to a gas. And then if you heat the gas up, it heats up normally. So a couple of questions here. First, what happens when you heat a substance up? The molecules move faster. This is why the temperature increases. But what happens during melting and boiling, as in what happens to the energy? First thing you say is the energy does not increase the kinetic energy. The speed of the molecules does not increase. Instead, the energy is used to either weaken or break the bonds in order to change state. That's it. So now that we've talked about changes in state, there's one more change in state we have to talk about, and that's evaporation. Because over here we said boiling is the change in state from liquid to gas. But there is another change in state from liquid to gas, and that's what we call evaporation. What is evaporation? Labina? Evaporation is the change in state from liquid to gas, but it happens at any, I thought I chose the pen here. It happens at any temperature. Any temperature. I don't care what temperature the liquid is at, as long as it's not boiling. Any temperature below the boiling point of a substance, the liquid can still change into a gas. That process is called evaporation. However, in terms of molecules, what happens? This is what happens. The most energetic molecules on the surface of the liquid, they break their bonds and they escape. What do we mean? من شوية احنا قلنا the temperature is defined as the average kinetic energy of the molecules in a substance. This means that some molecules in a substance already have a lot of energy. Some molecules in a substance already have a lot of energy, and some molecules don't. So some of the molecules that are already on the surface use that energy to break their bonds and they leave. Some of the molecules that already have energy, they don't need to be heated. Some of the molecules that already have energy use that energy to break their bonds and they leave and they escape. And that's how evaporation occurs. It's when the most energetic molecules on the surface of the liquid break their bonds and escape. This causes the temperature of the liquid to decrease. Unlike boiling, where the temperature is constant, the temperature during evaporation decreases. Why? Well, if most energetic molecules escape, there's less energetic molecules left behind, but the average kinetic energy of the molecules decreases. Yani I have molecules with less energy, so بالتالي the kinetic energy of the remaining molecules decreases. Yes. That's why the temperature decreases. That's why if I get some alcohol or perfume or something and I spray it on my hands, and as soon as it starts to evaporate, my hands feel cold. Not because the alcohol or the perfume is cold, but because when it hits my hand and it starts to evaporate, its temperature decreases, so it absorbs heat from my hand. Okay, next up, the last thing we want to talk about when it comes to evaporation is how we can make something evaporate a bit faster. Three very obvious things. One, you could heat it. So if you heat a substance up, the temperature would increase, so the molecules have more kinetic energy, so, faster evaporation. You could also increase the surface area, because increasing the surface area increases the number of surface molecules. The more molecules are on the surface, the faster the rate of evaporation. And finally, you could use air currents. And when I say air currents, I mean, something like a fan or air conditioner or just natural wind. When the wind blows on the top of the surface of the liquid, it pushes the molecules along with it. So instead of pushing the liquid down, like air pressure usually does, it just pushes the molecules away, making the evaporation happen much faster. So that's what you do if you want to increase the rate of evaporation. Obviously, the opposite applies. If you want to make something evaporate a bit slower, you either cool it down, so less energy, you decrease the surface area, or you don't use air currents. Cool? Cool. Okay, I'm gonna pause for a second. Let's go back to the questions. I want to see if any. Okay, first question. لو water is not pure, it will take longer to evaporate. Pure doesn't really affect evaporation much, just slightly, but it's not very important عندنا. Purity affects Ali, the melting and the boiling points. For example, ice melts at 0, water boils at 100. So if you have impure ice or impure water, the melting point will be a bit lower and the boiling point will be a bit higher. But دي حتة في الكيمستري أكتر شوية. He won't really ask us about that. Okay, next, no other caps lock questions في الحاجات القديمة. Okay, I see a couple new questions. Forgive me, I'm just putting a few more people in timeout because they become disruptive. Water is not pure. خلاص. هو temperature بتتأثر بالinternal energy. Yes and no, because think of it this way. Temperature increases when you heat a substance up, and when you heat a substance up, the molecules move a bit faster. فkinetic energy بتزيد. So technically, you could say that when you increase the temperature, the internal energy also increases. When you decrease the temperature, the internal energy decreases, because internal energy simply بيقول لك إيه الenergy اللي جوه. And temperature is affected by the energy اللي جوه. Next question. When surface area increases, does it also affect support air currents? They are two different factors. So لو temperature زاد, surface area increased, but the air current doesn't change, you will still have faster evaporation. They're different factors, but they do support each other. Can any juice get evaporated? That's a slightly silly question, Ali, but again, any liquid evaporates. Any liquid. Okay. Should you know what changes of state is exothermic, endothermic? That is chemistry and not physics, okay, Mixes? It's not physics, so no. مش علينا نعرف endothermic reactions و exothermic reactions. Okay, moving on. Thermal expansion. What is thermal expansion? If we look at the definition, it's the increase in volume of a substance when the temperature increases. This means that if you have a substance and you give it some heat energy, as soon as you give it heat energy, the molecules start to move faster, but they also move farther apart. And when the space between the molecules increases, as in they move further apart, the entire volume of the solid or substance increases. This happens all the time. يعني انت لما بيفور منك I don't know coffee على النار، لو انت بتعمل قهوة مثلا على النار, or you're like trying to boil some milk or something, you'll find the level of the milk increasing as it gets hotter because of thermal expansion. One very important thing to note is this: if you cool something down, if you decrease the temperature, the volume will decrease. We call this thermal contraction. So the molecules move slower in this particular case, and they move closer to each other. But when the molecules move farther apart or closer, this does not affect the bonds. Because a number of people love to describe thermal expansion, and they go ahead and say, yes, thermal expansion is the increase in volume and temperature increases because the molecules are moving faster and the space between them increases and the bonds become weaker. No, the bonds only become weaker or stronger during melting or freezing or boiling and evaporation. وقت الchange in state بس. Bonds are not affected by thermal expansion, all right? Excellent. But not all substances expand the same. Some substances expand more than others. Things like gases in general expand more than liquids if you heat them with the same temperature. Liquids expand more than solids if you heat them with the same temperature change. And that's because gases have no bonds or very weak bonds. Liquids have, slightly stronger bonds, in this case, strong bonds. And solids have very strong bonds. So all of them do expand. But if you're going to heat a solid by, I don't know, 1 degree or something, maybe it'll expand this much, which is almost nothing بالنسبة لكم على البورد. If you heat a liquid, it expands much more for the same change in temperature. If you heat a gas, God help us, because it expands a lot. A lot. Okay. Now, expansion is a pretty simple concept. We are going to use this again. This is going to be very important later on when we talk about convection. All right. But let's talk about this. Cases where thermal expansion is a problem. There are a few cases where expansion causes issues, especially when it comes to certain types of buildings or designs. First would be railway tracks, قضبان القطر, or a metro. Usually when they build tracks, they often build these long rails or tracks, and they leave small spaces between each section of the rail and the next. They do this so that they can account for thermal expansion. عشان لما الصيف يجي and the temperature rises, this piece of metal expands, this piece of metal expands, this piece of metal expands, and they fill the gaps. And when the temperature, drops, it contracts and opens up the gap again. So what would happen if you have a nice super long railway track? Well, what happens is this: because it's larger, and if you heat it, even if you heat it the same amount, because it's a much longer piece in one shot, it expands more. The expansion increases even more. Usually railway tracks are fixed at their beginning and the end. So if you do not allow a railway track to expand, it will expand بالعافية. Like it'll expand even if you don't want it to. But instead of expanding and filling up gaps like it did here, nope. It expands and it starts to deform and curl like this. It's not good. This is really bad. Because this means that any train that tries to move over that track is going to derail. An identical issue would be bridges or roads. Usually when it comes to bridges and they build a bridge, they also build bridges in sections. If you live in Nasr Al-Jadida, Heliopolis, you're going to be very familiar with the construction of bridges now. You should be a professional by now. And you're going to notice that they always build the bridges in sections. Now, excuse the exaggeration here. Obviously, I'm exaggerating on the screen, but so they do leave a small amount of space between each section. For the exact same reason we left spaces between railway tracks, to allow for expansion. عشان يحصل expansion during the summer ويملى الحتة دي. يحصل expansion during the summer ويملى الحتة دي. And then during the winter, it contracts and opens up again. And that's thermal expansion. Okay, excellent. Before I move on to gases, quick look at the questions. Okay. ما فيش questions. Why is there space between what, yeah, Ali? Please make sure to clarify your question a bit more. Okay. Looks like this section is quite easy, so let's move on really quick. Make up for lost time that we lost in the beginning of the session. Now we're going to talk about gases, and the first thing we want to talk about is something called Brownian motion. Brownian motion is quite simple. If you take a smoke cell, which is basically just, a glass box with smoke inside. This smoke could be from, I don't know, bukhur, or maybe Mr. Yu was smoking a cigarette or something. I do not condone that, by the way. But let's just say he has something that's smoking in his hands, and it's currently emitting smoke. Remember, bukhur. Mr. Yu's back. And he decides to put that smoke inside a glass box. If you trap some smoke inside, smoke is basically just little pieces of dust and hot air. So if you take that smoke and you put it inside the box, and you put that box on a microscope, the microscope lights up the smoke box, and you start to see small, what we call specks of light, just small dots of light moving around freely, but in a very odd manner. We say they move around randomly, as in they change directions randomly, and jerky or irregular motion, meaning they do not curve. No, that's not what they do. They just suddenly change direction, as if they're moving and suddenly they change direction. This is called jerky motion. The question is, these dust particles are solid, and solid molecules actually want to vibrate and they want to just sit down and rest. So the question is, why do they move? And the answer is quite simple. Around each dust particle, there are lots and lots and lots of tiny air molecules that are moving around freely. And when these air molecules are moving around freely, they collide with the dust particles. And the dust particle starts to move because it's being smacked around. Just a second. There we go. This dust particle starts to move because it gets smacked around by the air molecules. So what is Brownian motion? It's the random and jerky motion of dust particles. Sometimes we don't use dust, we use the word smoke. The random and jerky motion of smoke particles in air. And how does it occur? Or why does it occur? Because the air molecules, as they're moving freely, they collide with the dust particles, or they hit the dust particles. And that's what causes the smoke or the dust to move. The order in which we mention this, or we say this in an answer, is important. مش الدست اللي بيروح يخبط السموك. I'm sorry, مش الدست اللي بيروح يخبط الاير. لا. The air molecules are what go hit the dust. خلاص? So the air molecules hit the dust. Next. This opens up an idea. The idea that air molecules or gas molecules move freely. And as they move freely, they obviously collide with each other and the walls of a container and so on and so forth. So this means that gases apply pressure. How do they apply pressure? Because as the gas molecules move, they keep hitting the walls of these containers. And when they hit the walls of the container, they apply a force over the area of the container. Because if you remember, in Unit 1, pressure is force over area. So if you're applying a lot of force over a large area, which is basically all of the container, you apply pressure. And that's how a gas applies pressure. Now, if you change the speed of the molecules or the space between them or the surface of this container, you can also change the pressure, and that's what we'll talk about now. Year 10 students, ركزوا معايا الحتة دي year 10 بقى. Remember that when something collides with something else, any two objects collide, like the air molecules collide with the walls, they experience a change in momentum, and that's what causes the force. In your answers, you must add this. This is worth a mark. Okay. We're now going to talk about 3 gas laws or 3 behaviors when it comes to gases. The first is how does temperature affect volume, and that's what we called, you guessed it, thermal expansion. Thermal expansion is the increase in volume of a substance when the temperature increases. And as we said, the molecules move faster and they move farther apart. But unfortunately, because we can't see gases very clearly, we kind of need something to help us see gases clearly. We get what we call a piston cylinder arrangement, or a syringe أو سرنجة يعني من الآخر, that's closed off at this end. It's blocked. الحتة دي مقفولة. There is air inside, and when you heat this air, the molecules move faster and they move farther apart, and the volume of the air increases. So when the volume of the air increases, it pushes the piston out. So you can now see the thermal expansion of a gas, since it's impossible to see a gas or air with your naked eye, just to be specific. However, please note that during thermal expansion, even though we're heating the gas, the pressure stays constant. The pressure does not change, and that's because the space between the molecules increased. You allowed the molecules to move farther apart. Sure, they're moving faster, but they're not really hitting the walls any harder or more frequently because you allowed them to move farther apart. Okay, that was thermal expansion, but what if we do not allow the gas to expand? What if you trap the gas in a fixed container, as in you keep the volume constant? If you keep the volume constant and you increase the temperature and I start to heat it up, remember, we already said the molecules are moving around and they're colliding with the walls, عايشين حياتهم. But when you heat them up and they move faster, they want to move farther apart, but unfortunately for them, you've trapped them inside the container. So they start to move faster and they start to collide with the walls much more frequently, and they collide with more force because they are moving faster. So if you heat a gas up and the volume is constant, the pressure is going to increase. Why? Because the molecules move faster, so they collide harder and more frequently with the walls of the container. So we just simply say that temperature and pressure are directly proportional. Okay? Excellent. Finally, what if you don't heat anything at all? What if you keep the temperature constant? Like, I'm not going to heat the gas up. You're going to get the same piston, but you're going to push the piston inside. So when you push the piston in, you force the molecules to be closer to each other. And when they're closer to each other, and the space between them decreases, they're not moving faster. Please note, they're not moving faster. They're just colliding with the walls more frequently. It's like I trapped you in a smaller room, so you don't have much room to move. So you keep hitting the walls more often. And this causes the pressure to increase. So when the volume of the gas decreases, the pressure increases because the molecules are now closer to each other. There's less space. So they collide with the walls more frequently. Remember, it's not faster and it's not harder, it's just more frequently. Okay, excellent. So now we've taken 3 gas laws. So again, if you increase the temperature of a gas, the volume will increase, but the pressure stays the same. However, if you heat a gas and the volume is the same, the pressure will increase. And if you're not heating at all, but you decrease the volume, the pressure will increase. So these are all things that affect pressure. Okay, this next equation is not for year 9s. So to the year 9 of you, this is an equation that your 10 students are only going to be using. P1 V1 equals P2 V2. What is this? It simply says that the pressure times volume before you compress the gas is equal to the pressure times volume after you compress the gas. It stays constant. Let's solve a quick example. So if I tell you that we have this piston over here that we had before, and here's a piston cylinder, the syringe, and the initial volume is 20 centimeter cubed, and the pressure inside is atmospheric pressure, so it's about 1 times 10 to the power of 5 Pascal. I want you to calculate the pressure if you compress the piston, as in push the piston in, until the volume is about 5 centimeter cubed. Remember, you've now decreased the volume, so you should expect the pressure, the new pressure, to increase. And here's how we solve it. First, the equation. P1 V1 equals P2 V2. Second, identify your P1s and V1s and 2s. So this is P1, this is V1, this is V2, and you're looking for P2. And finally, just substitute them into the equation. Just plug them into the equation. So 1 times 10 power 5 times 20 equals P2, because we don't know it, times 5. So this leaves us with P2, if I just rearrange the equation really quick, times 20 over 5. 20 over 5 is 4. So this gives us a final answer of 4 times 10 to the power of 5 Pascal. Or you could just say 400,000 Pascal if you do not like SI units, or if you don't know how to convert them from your calculator. Here. Excellent. Okay, so now we finished talking about the behavior of gases. I'm gonna pause for a second, check questions. Okay. In the last law, can we see the total force increased? You could say that, yes, because the number of forces have increased. So yes, the total force is increased. But I would prefer that you just mention, Malik, that the molecules just collide more frequently. Okay. How is the pressure constant in this range if it's increasing in area? Yeah, here's the thing. Remember, pressure is force over area, and you're right to think or to ask about how is the pressure constant if you're increasing the area. Let's go back. Sure, the area is increasing. Like, I'm with you. The area here has now increased. So according to the rule, pressure equals force over area. If the area increases, the pressure should decrease. However, please remember that you're also heating the molecules, so they're moving faster and they're colliding harder. So the force also increases. This means that if the force increases, the pressure should also increase. However, if the area increases, the pressure also decreases, so you get no change. It's both increasing and decreasing at the same time. And that's why the pressure stays constant. Can a gas expand infinitely? Theoretically, Lily, yes, but there are things in physics, higher level physics, which we have not studied yet. So for now, I'm just going to say sure. In our case scenario, it expands infinitely. Mr. Why is dust heavy? Dust isn't really heavy. Dust is a solid, and depending on how much dust you have, it could either rest or not. Malik, can I increase the gas pressure in the rate of change momentum Hall force? Yes, Malik Muhammad, that is right. If you increase the temperature or any kind of pressure causes any increase in pressure is due to the increase in force in this case, and it's due to the rate of change of momentum, which is the force. Malik Muhammad says increase the volume by pressing Alt F4. Sure thing, Malik. Oops, I accidentally put you in timeout too. Okay, so let's continue. Okay. Next up, after we were done with that, let's talk about conduction, convection, and radiation. This class might last a bit shorter than I expected, but that's still good because it leaves me with time to, try and solve a few questions. We have 3 methods of heat transfer when it comes to heat going through substances, either conduction or convection or radiation. Conduction is mainly the transfer of heat through solids. Convection is the transfer of heat through liquids or gases, and radiation is just through everything else. But before we talk about them, what is conduction? Like we said, conduction is the transfer of heat through solids, but that's not the real definition. It's the transfer of heat through the vibration of matter, but without the transfer of matter. What do we mean by that? Since it mainly happens in solids, assume that I have a nice long solid bar. You can see this in front of you right now. And if I start to heat it up, like if I start to give heat energy to this first set of molecules, these molecules start to get hot and they start to move faster. But since it's a solid, they only vibrate. And when they vibrate, they start to collide with the next set of molecules. When they collide with them, they give them heat, which causes them to also vibrate, colliding with the next set of molecules, which gives them heat, colliding with the next set of molecules, which gives them heat, colliding with the next, and so on. So you haven't noticed the molecules didn't really move from their spot. They just vibrated in their own spots in place, and they started giving heat to the next and next and next and next and next and next molecules. So that's conduction in a nutshell. It's quite simple, really. But we have two different types of conductors, good conductors and bad conductors. Good conductors are things like iron, copper, steel, aluminum, I don't know, nickel. Basically, all metals are good conductors. And that's because metals actually have something else inside them. They have what we call free-moving electrons. Free-moving electrons. What do? Well, when you heat the substance up, these electrons gain heat energy, and they don't really need to wait to vibrate and hit the next molecules. They can just move freely inside the metal. So since they're moving freely, they can just collide with all of the atoms in the way, heating up the metal much, much, much faster. This is why metals are really good conductors of heat. Again, of heat. What are examples of bad conductors? Well, that's another easy question, or easy solution here. Plastic, rubber, wood, glass, basically non-metals, wool. All of these are bad conductors of heat, which we also call insulators. But three things to note. Air and water are really bad conductors. They do not conduct heat very well. They transfer heat through convection, which we will see in a bit, but they're not good conductors, okay? A vacuum, however, is what we call the perfect insulator. It does not conduct at all because a vacuum has no molecules inside. There isn't even a single molecule to transfer heat, so we say vacuum is a very, very bad conductor, or the perfect insulator. Okay. Since air and water, or liquids and gases, do not conduct very well, they obviously transfer heat through something else, which we call convection. Convection is the transfer of heat through liquids and gases, and it kind of depends on thermal expansion here. Now, why? Follow closely the sequence. This is important. If you start to heat the liquid here by heating this side with a Bunsen burner or a contact heater or an electric heater, I don't care, and the liquid here becomes hot, when the temperature of this particular liquid increases due to conduction, because remember, it's touching the heater, the volume increases, as in it expands. And when the volume increases, it becomes less dense. Its density decreases. And this is important. Remember, density is equal to mass over volume. Usually, the density of a substance is always constant. However, when you heat something up, the mass does not change because temperature doesn't really affect mass, but the volume increases. And when the volume increases, its density decreases because these are inversely proportional. So because this liquid is less dense compared to the rest, it starts to rise up and it fills up the upper part of the liquid. Now, the liquid that is cold, let's just say it has a low temperature, has slightly less volume, which makes it slightly more dense. So because the cold liquid is more dense, let's change colors here, because why not? We have the ability to. Because the cold liquid is more dense, it sinks down and fills up the bottom half of the container. So what happens is that the cold liquid sinks, whereas the hot liquid rises. The hot liquid rises. Okay. So cold liquid sinks, hot liquid rises, and you end up with a cycle which we call the convection current. Okay? Please note you have to mention the whole idea of density changing and the fact that liquid rises and drops if he ever asks you to describe convection. Don't be lazy and just talk about the molecules. Talk about the molecules when he asks for them. But if he asks for, hey, describe how convection occurs, you must mention how the density changes. The hot liquid is less dense, so it rises. The cold liquid is more dense, so it sinks and creates this current. That's it. That's all we need to say. Okay. Great. I'm just going to go back to questions really quick. So, we have a first question. Mr. Daf, liquid best? No. It's not just liquids. It's liquids and gases. Let me explain this again, but using gases. Unfortunately, we're going to have to block a few people from the chat. Because they're being very disruptive. Next, مش لما temperature بتزيد ال potential energy بتزيد. Yes يا مالك, potential energy also increases because the space between the molecules increases. Malik also asked, can I add in gas pressure? Oh, لا, that was an older question. So we're done with the questions here. Great. Why does the less dense liquid rise? Because here's the thing. Density, Aziz, affects how objects rise or fall. Density affects how things rise or sink. When you have an object that is less dense than the liquid it's in, it floats on top of that liquid due to a force called upthrust, which we will talk about in Unit 1. So when something has a low density or a lower density than the liquid it's in, it experiences a lot of upthrust, so it floats, so it rises up. Whereas when something is more dense, like it has a large density, it's more dense than the surrounding liquid, so it has a lot of weight compared to the upthrust, so it sinks. That's why things float or sink. Density decreases. Yes, when you heat something up, Pablo, density decreases, Marwan. And when you cool it, the density increases. Yes. Where are the more dense particles? Lujain, this is very important because thank you for pointing that out. There is no such thing as more dense or less dense particles. There is something called a more dense or less dense liquid, because if you remember, density is mass over volume of the substance. But when it comes to the particles are either close to each other, which makes this substance more dense because it has a small volume, or the molecules are far apart from each other, which makes it less dense. And this has a lower density, this has a higher density. Never say more dense or less dense particles. Say a less dense or more dense liquid or gas, but not just particles, okay? Plus, they're not anywhere. They're part of the liquid. They just rise up together or they sink together. Okay, since nobody else is asking any questions, so let's move on. The voice will probably diz just a bit because when we were facing that previous problem, I kind of changed my microphone. So, turns out it wasn't the microphone, it was the, my PC itself doing that problem, that weird thing of looping the audio. So next time I'll just use my better microphone. Okay, finally, the last type of heat transfer is called radiation. Radiation is the transfer of heat from the surface of any object. Any object emits radiation. I don't care what it is. If you have a cup of coffee or tea, I kind of need a cup of tea. The surface of that hot cup of tea also emits radiation, heat. If you have, I don't know, let's say your phone, and you're busy playing games on your phone instead of listening to this lesson properly, you know, like Raid Shadow Legends or something. I don't know what you're playing. And it's going to be emitting heat because, you know, it's getting hot. You're playing way too many games on the thing. Or maybe you have, I don't know, Mr. U. Mr. U ده قاعد في الصيف, you know, الجو حار, he's sweating, and his body is emitting heat from the surface of his, you know, skin. All of this, all objects emit radiation, and we call this type of radiation infrared radiation or waves. Now, infrared waves or rays are just a type of electromagnetic wave. As we've revised before, it's just the transfer of energy, and it transfers heat energy. Since it's electromagnetic, it can go through a vacuum. A vacuum. Which means it doesn't really need matter. So can it go through, you know, air? Yeah, sure. Can it go through liquids? Why not? Depending on how, you know, dense it is. Can it go through solids? Sure, but if we're talking about a solid like, I don't know, glass or something, but usually solids kind of stop radiation. But if it's, you know, glass or something, just treat radiation or infrared waves like light. If light can kind of go through, then the heat would probably go through. Now, the amount of radiation something gives out depends on a couple of things. Number one, it depends on the temperature of the substance. And number two, it depends on the color of the surface. If the temperature increases, the amount of radiation increases. So if I have a hot cup of coffee, like this cup over here, it's going to emit a lot of radiation. But if I leave it up in the air for a bit and it evaporates and it cools down and, you know, emits radiation and such, and temperature decreases, it's still going to emit radiation, but a lot less. So the higher the temperature, the greater the amount of radiation you give out. And the second is the color, and this is really good, important too. Black is what we call the best emitter and absorber of infrared waves, whereas white is the worst absorber or emitter of infrared waves. But before we talk about the best or worst, what do we mean by emitter and what do we mean by absorber? An emitter is something that's going to give out heat. Yani, an emitter means the object is hot and is going to give out heat. An absorber implies that the object is cold or colder than surroundings, so it's going to be absorbing heat from the surroundings. We say the black is the best emitter and absorber of radiation, whereas white is the worst absorber and a emitter of radiation. Take a look at this experiment over here. If I get a heater, just a random heater, Bunsen burner, flame, electric heater, it doesn't matter, and I put it between 4 cans, and each can is painted in a different color. One's dull black, one's dull white, you know, matte, dull or matte. One's shiny, or reflective, metallic, as you can say, black, and one's shiny white. Remember, this heater is emitting heat to all of them. And you want to see which one becomes hotter, faster. Because remember, all of them are going to be absorbing heat from the heater. Like the heater is going to emit heat equally to all 4 of these objects because they're all placed at the same distance from the objects. The one that's going to heat up the fastest would be the dull black. Like this is going to heat up the best. Whereas the worst is going to be the shiny white. This is going to be the worst. They're still heating up. You need to realize this. They're all heating up, but the one that's going to heat up the best or the fastest would be the dull black. That's why they usually tell you in the summer, don't wear black t-shirts or something, because if you walk in the sun, it's going to absorb the infrared rays much faster and you're going to, you know, feel hot. But I don't care. I like wearing black t-shirts myself, summer or winter. But it's smart if you kind of want to, you know, stay cool during the summer, just wear brighter colors. If you want to stay warm during the winter, wear darker colors, because when you sit in the sun, I usually like doing that during the winter, sitting in the sun. It's so comfortable. When you sit in the sun, you can absorb heat faster or slower. Okay. Excellent. give me a moment يا جماعة كده. Okay. So that was radiation. Let's just talk about emission for a bit. A second experiment which he usually likes to ask about is this one. Let's just erase all this. This one. In this particular experiment, what we do is we get a box, a single object, and we're going to fill it up with hot water. Like if you fill this up with hot water, each of these surfaces is going to emit radiation. Each one of these surfaces is going to emit infrared waves. And the hotter the surface, the more infrared waves it emits. So for example, this side is going to emit heat, this side is going to emit heat, this side is going to emit heat, the back side is going to emit heat. But the one that emits heat the most will also be the dull black side, the matte black side, because black is a really good emitter. It allows heat to flow in and out freely. Whereas the worst emitter is going to be the shiny white. It's going to emit the least amount of heat. So for example, I'm sorry, here's the shiny white. So this emits the least amount of heat, this emits the most. So if I ask you, which color heats up the fastest, you'd say dull black. Which color would cool down the fastest? It would also be dull black. Okay, great. Now, we'll move on to thermometers, but before I do, I'm going to do a couple of things. We're going to take a look at the questions, and we're going to take a very short break so that I can get a drink. But before that, questions? First, this is year 10. This is both year 10 and 9, both, okay? Because ما فيش فرق كبير ما بين الاثنين. The year 10 parts are going to show up at the very end, and that's when I'll let you leave. I'll let the year 9 students leave. ينفع تعيد حتة surface temperature. أحمد يا وليد, basically what happens is this. When the temperature of any surface increases, it has more energy to give out. So you emit more infrared waves, so the waves become stronger. So when the temperature of the surface increases, let me go back to the radiation slide. When the temperature of the surface increases, the amount of radiation gives out also increases. Next, Chris asked me something, but he deleted this message. Omar is asking, يعني لو في السؤال in winter, what's the best color to paint the house? Here's the thing. Usually we don't ask about winter. We often ask about summer more because it's the easier thing to do. Because winter, it depends. If your country is always cold, then it would be probably, and there's sunlight, it's preferable to have it darker so that you can absorb some of that heat. But there are other factors to keep into consideration, Yamar. So he doesn't usually ask about winter homes. He usually likes to ask about summer homes. Is there going to be session 4.1? Yes, Sana, please check the schedule. There's going to be a session on 4.1 tomorrow, I think. Yes. Tomorrow is the first session for 4.1, for unit 4, basically. We'll talk about electricity tomorrow and magnetism the day after. Why do hotels use shiny silver containers in their buffet? Well, because you don't want the containers to cool down fast. If you go to a buffet, and it's been a while since I've been to a buffet, but if you go to a buffet, you're going to find that the containers are all nice and shiny and silver. And that's because they don't want them to lose heat. They're busy heating them up with, candles or small heaters beneath them, but you don't want them to lose heat very quickly. So silver is the best. Besides, they usually make them out of metal and it's a hassle to paint it. Okay. Excellent. So we only have the thermometers section left and finally the calculations, but for the time being, let's take a short, 2-3 minute break. And when we're back, we're going to talk about, a few more things, thermometers and heat energy calculations. Okay, cool. Be right back. We're going to continue from where we left off. Okay, so Just a quick test. I'll take a look at the chat one more time and check if some people have questions. Dork. Somebody sent me a question on WhatsApp really quick كده. He was asking, when does an object decide to absorb or emit radiation? If black is the best at both, when is it emitting, when it is absorbing? As I said, an object emits when it is hot, because it's hotter than the surroundings. It has more radiation than the surroundings, more heat than surroundings. So it loses heat to the surroundings, whereas an object absorbs when it is colder than the surroundings. Okay? Good. Great. So let's move on. First, let's talk about thermometers. What is a thermometer? A thermometer is an instrument that measures temperature. There's nothing special about it, it just measures temperature. But the question is, how does it measure temperature? If you have a beaker full of a liquid, let's assume that this liquid is currently at 20 degrees Celsius, you're gonna find the reading roughly about here. If you start to heat this liquid up, and let's say it heats up to, I don't know, 100 degrees or so, you're gonna see the level inside the thermometer rising until it stops at 100. So it rose from 20 degrees Celsius to 100 degrees Celsius. What showed you the temperature was the expansion of the liquid. The volume of the liquid is what showed you the temperature. Again, the expansion of the liquid is what showed you the temperature. So the more you heat things up, the more it expands. And the more it expands, it simply shows you a higher temperature. So any thermometer makes use of quantities that change with a temperatures. And here's a quick list of things that we've seen these before, but here's a quick list of quantities that do change with temperature. Things like solids and liquids and gases. All of these have volumes that change with temperature. The pressure of a gas changes with temperature. Remember, when temperature increases, the pressure will also increase. The resistance of a thermistor, we'll review this again next time, but if you remember, when temperature can be Z, the resistance would decrease. They were inversely proportional, so we could kind of make electrical thermometers using these. And the voltage across a wire, that also changes with temperatures. However, to the year 9 students, this is not for you. Okay? Cool. Next, let's talk about calibrating a thermometer. How do we calibrate a thermometer? And what do we mean by calibrating? We have a scale called the Celsius scale. This is a temperature scale that a guy called Anders Celsius created. We use it all the time. Like, for example, if I open up my phone right now and I check the temperature, it says 18 degrees Celsius. It's not bad, actually. Although it's kind of hot in here because I have to close off everything in this room to minimize the noise as much as I can. But still, 18 degrees Celsius is pretty cool when it comes to temperature, that is. But how did Celsius create his scale? He did so by a process called calibration. He created 2 fixed points, which he called the upper and the lower fixed points. So he has this nice long empty scale, which is not empty in front of you guys, and he marked 2 points on them. The lower fixed point is actually 0, which is the temperature of pure melting ice. And the upper fixed point is 100. So what we do first when we have this nice empty thermometer is that we take the thermometer and we place the bulb inside a beaker full of pure melting ice. That's what we first do. We put it inside a beaker full of pure melting ice. And when the temperature level drops, we just create a mark over here and we number that as 0. Then we take the thermometer, you put it in a beaker full of pure boiling water. It's got a lot of steam. Sometimes we even put it in the steam itself, like sometimes we put the thermometer over here, like right above the water so that the steam hits it as it rises. And we mark the upper level over here and we number it as 100. Those are our lower and upper fixed points. What we do next is this. We measure the distance between these 2 points Then we measure the distance between these 2 points, and we divide it by 100, so we can get 100 little divisions that we start to make. And that's what we call the Celsius scale. You must use pure boiling water and pure melting ice, because as Ali asked a little while ago, do impurities affect anything? Well, yes, they affect the boiling point and the melting point of ice. The boiling point of water is 100 degrees Celsius. The melting point of ice is 0 degrees Celsius. If they're pure. If they're impure, like if you have any salt or anything else in the water, minerals and stuff like that, it changes these levels. So it has to be pure distilled water. Okay? Excellent. And with that, year 9 students, feel free to leave, because this next final section, over the next 10 minutes or so, this is only for year 10 and 11 students, okay? So year 9 students, if you have any questions, I'll just take a look at them. Now. Otherwise, feel free to leave. Okay, excellent. Goodbye. I'll check my WhatsApp really quick, because some people do like to ask questions on WhatsApp, not on the chat over here. Excellent. Awesome. Okay, so goodbye, year 9 students. It's been great having you here. What if the scale starts from -10? No. If the scale starts at -10, the lower fixed point is still 0. The -10 is just the lowest temperature you can measure right now, but the fixed point is still called 0. Do I write with the mouse? No, I have a drawing tablet, and I suck at using it, so it's مش فارقة كتير ما بينها وما بين الماوس. Okay, let's move on. Now, when it comes to using a thermometer, there are different properties that we have to be aware of when it comes to buying or using a thermometer. The first thing is called its range. The range is the smallest to the highest temperature a thermometer can measure. For example, in this thermometer, it can measure from 0 to 100, so it has a range of 100. But sometimes we have thermometers that measure from -10 degrees and maybe to 110 degrees. This simply means it has a higher range, from -10 to 110. So that's the range of the thermometer. Sensitivity is defined as the smallest change in temperature that the thermometer can measure. This means that if we zoom in to the thermometer really close, we'll notice that every division represents 1 degree Celsius, a 1 degree change. And that's the sensitivity. And in this case, this thermometer can measure. Oops, the pen's not working. 1 degree Celsius. That's the smallest thing it can measure. That's its sensitivity. Some thermometers can measure up to 0.01 degrees Celsius. It's really accurate or sensitive, as we say. And that's what sensitivity means. It's the smallest change. كل division هنا بكام. Next, response time. I think this one is kind of self-obvious. It's how much time it takes to detect the change in temperature. Like, for example, if you take this thermometer and you shove it in your mouth, how long do you have to wait before it gives you that reading or your temperature? That's basically response time. And finally, linearity. Linearity is simply a property that you need a thermometer to have. It's a property that you need a thermometer to have. It's the fact that the change in property is directly proportional to the change in temperature. Meaning, if you heat this bulb up, and you heat it by 1 degree Celsius, and you change it from, 1 to 2, and it expands 1 millimeter. This means that if you heat it to 2 degrees Celsius, it should expand 2 millimeters. 3 degrees Celsius, 3 millimeters, and so on. This means that the change in temperature and the change in property, the expansion, have to be directly proportional. The reason we call this property linearity is because if you draw a graph of how the temperature changes with the, length of the thermometer or the liquid inside the thermometer, it will give you a straight line starting from 0 and 0. Okay? So that's pretty much it. So what's linearity? It's the fact that the change in temperature and length are directly proportional. Now, there's a big difference. If he asks you a question, there's a big difference between what is linearity and what does the term linear scale mean. Linear scale simply means that the spaces between the molecules are equal. Like it's an equally divided scale. This is only possible if the liquid we're using, the mercury that we're using inside this particular tube, is linear. Okay? Right. So these are the 4 different properties that we can change depending on the size and shape of the thermometer tube itself. So let's talk about the thermometer tube itself and how we can affect or change the properties with it. Okay. Let's move on. This is a liquid glass thermometer. شفناها كتير قبل كده. This thing is called the bulb. This is called the tube. Sometimes we call the liquid inside the liquid thread, okay? It doesn't really change anything when it comes to its use, but دي تسمية مش أكتر. Now, there are 3 things I can change in a liquid glass thermometer. 1, I can change the length of the tube. I can make it longer or shorter. Number 2, I can change the diameter of the tube. I can make it thicker or thinner. And 3, I can change the size of the bulb. And we want to see what each one of these 3 things do. First, what does changing the length do? If you increase the length of the tube, if you change the length of the tube, the range increases. Why? Because if you have a tube and you make it longer, instead of it reaching, for example, 11 degrees or so, it could reach 12 now, it could reach 13, it could reach 14, it could reach 15. So the longer the tube, the more range you get. Now, that's great and all, but if you make the tube too long, it might break, so not a good idea. Not all the time, yeah. Okay. Second, if you decrease the diameter of the tube, if you make the tube thinner, the sensitivity will decrease. Oh, sorry, increase. There's no undo option, unfortunately, so sensitivity will increase. It will become more sensitive. But this also causes the range to decrease. Now, why? Take a look at the 2 diagrams here. Take a look at these 2 thermometers. The first thermometer has a range of up to, in this particular space, 110 degrees Celsius. That's the farthest it can go. It's from -10 to 110. And the single division is 1 degree Celsius. But if you get a slightly thinner tube, if I decrease the thickness of the tube, what happens is that that same 1 degree Celsius needs more room to expand. It needs to expand a longer length, which gives you a sensitivity of 0.1 degrees Celsius. Each division here, I'm sorry, the pen blacked out for a second. Each division here on the thermometer scale is worth 0.1 degrees Celsius, whereas each division here is worth 1 degrees Celsius. So it's more sensitive. Because you made it thinner, is more sensitive. But because you made it thinner, the maximum temperature you can now reach is lower. Because instead of the 1 degree taking up this much space, or the 10 degrees, let's look at 10 degrees. 10 degrees take up this much space. 10 degrees in the thinner thermometer take up a lot more space because it has to expand along the length of the tube. So the range decreases. So that's what happens when you decrease the diameter. You increase sensitivity, but you decrease the range. And third and finally, the bulb. If you increase the size of the bulb, the sensitivity increases just like the diameter. Let me just erase this for a second. And the range decreases exactly the same what happened with the diameter, because the liquid now expands more, because when you have a bigger bulb, you have more liquid, and the more liquid you have, the more it wants to expand for the same change in temperature. So that increases its sensitivity, decreases the range, and increases the response time. It takes more time to give you that change in temperature. So it's not always a good thing to, make the bulb bigger or smaller. It's always best to change the length of the tube if you want to change the range, or the diameter of the tube if you want to change the sensitivity. Okay, great. That was the thermometer. Oh, and the final point, just so we don't forget, there are two liquids that we could use here. We could either use mercury or we could use alcohol. We often use mercury, however. Okay, question time. Okay. Okay, next. Omar, yes, your 9 can go. Why was I placed in timeout? Because you guys were getting kind of angsty. Okay, no other questions? Okay, great. Let's move on to the very last bit when it comes to thermometers, the thermocouple. Thermocouple is simply a thermometer that is digital. It doesn't use the expansion of a liquid or a solid or anything else. It's made of two wires. So you have one wire up here. It's copper, iron, steel, choose whatever metal you want. And you have a second wire down here, and they're joined together at the two ends. We call these the junctions. A junction is just the meeting point of the two wires. So what do we mean by junctions? As we said, just the meeting point of wires, but it's called a thermocouple because you have two different wires of two different materials. If you haven't noticed, this is made of copper, the other is made of iron. Or you could have the upper wires made of iron and the lower wires made of copper. You could have the upper wire made of steel and the lower is made of aluminum. I don't care, as long as you have two different wires. So when you do this and you heat one end and you cool the other, and there's a temperature difference between the two, you end up with a reading on the voltmeter. And the bigger the temperature, the greater the temperature difference, the greater the reading on the voltmeter. So the more you heat it up, the greater the voltage increases. So the property that we're using here to measure temperature is voltage. It's the change in voltage. And thermocouple is what we actually use when we measure the temperature of our bodies. عارفين thermometer اللي هو digital that you hold and you press a button and you put it in your mouth. If you try to break that, and I'm not telling you to break it, I'm just saying if you break that, you won't see any liquid or something inside. اللي هو digital You'll find a couple of wires of different colors, and they're just joined at the end في الحتة الميتال اللي برا دي that you put in your mouth, connected to a little circuit اللي هي الحتة اللي فيها الفولتميتر بقى. That's pretty much it. It has a lot of advantages over a regular thermometer. It's very robust, it doesn't break, so if you drop this, nothing happens. It measures things very quickly because here's the thing, since they're made of metals, these two junctions are made of metal, they have a very small heat capacity and they're very small in size برضه في نفس الوقت, which means it's very easy to get very quick measurements and accurate measurements. It has a wide range. Since we're using metals like copper and iron, just to let you know, iron has an approximate melting point of around 1500 degrees Celsius. يعني أقدر أقيس temperatures up to 1400, 1450 degrees if I'm using iron. So it has a very large range. And you can measure things from afar, meaning أنا ممكن أحط مثلا hot junction جوه فرن. Let's say I have a nice big oven اللي بنعمل فيه العيش. If you've gone to TBS قبل كده هتلاقوا دايما عندهم أكياس كبير كده عامل زي التلاجة, but that's actually an oven. بيحطوا فيه الحاجة ويقفلوا الباب عليه والعيش بيتعمل جوه. And they always have a screen outside or multiple screens outside tell them the temperature, the time and stuff like that. Usually ده بيبقى thermocouple, بيبقى فيه wires جوه بتقيس التمبرتشر وبتشوف انت reading بره. فمستر يو اللي شغال في TBS, the bakery station اللي ميعرفش يعني TBS, بدل ما هو يمسك في ايده thermometer ويحطه هو جوه وهو سخن, let's say 150 180 200 degrees ساعات ويتلسع ولا حاجة, لا, he just looks at the reading on the scale ويبقى مستريح. Okay, that's a thermocouple. Yeah. The last thing we need to discuss هم energy calculations. We have two equations that we use, but before that, a quick and final look at the question before we finish this section. Hagar, if the tube is not smooth, what would happen? The tube has to be linear, flat, and smooth. Linear, flat, and smooth. So مفيش نقاش في كده. Because if it's not linear or constant in diameter, the linearity will not be constant. It will get messed up. So that's not what we want. Okay, any other questions? Okay, none so far, and nothing on WhatsApp either. So let's finish this up. Let's finish this. Let's do this. Okay, Leroy Jenkins to everybody who gets the reference. Leroy Jenkins. What is the equation that we use to calculate heat energy? This is it. E equals mc delta T. What do they represent? E is the energy. You're looking to calculate how much energy you need to heat something up. M is the mass of the substance. And delta T, and the triangle, this is called the delta, means change in temperature. Change in temperature. Okay, so E equals mc delta T. If you want to calculate the amount of heat energy something needs, it depends on the mass, which makes sense. The more mass I have, the more energy it needs. If I have a cup of water in my hands right now and I want to heat it up, it will depend on how much water you have and what change in temperature you want to apply. عايز تسخنها أكتر, it'll need more energy. But it also depends on the material or the substance you're heating. Are you heating water? Are you heating oil? And that is represented by the quantity called specific heat capacity. It's defined as the, let's zoom in here, the amount of heat energy needed to raise the temperature of 1 kilogram by 1 degree. 10. The amount of heat energy needed to raise the temperature of 1 kilogram of a substance by 1 degree. The unit of measurement of specific heat capacity is joules per kilogram degrees Celsius, or sometimes it's joules per grams degrees Celsius. For example, if I tell you that water has a specific heat capacity of, let's say, 4,200 joules per kilograms degrees Celsius. This means that if I have 1 kilogram of water and it's currently at 20 degrees Celsius, and I want to heat it up from 20 up to 21 degrees Celsius, that's a 1 degree change. How much heat energy do you need? And that would be 4,200 joules. So it kind of tells you الماتيريال بيحتاج energy قد ايه. Like it specifies, it's very specific, it specifies نوع الماتيريال that you're trying to heat. طبعا this is a general value, because what if I don't want to heat 1 kilogram? What if I want to heat 10 kilograms of water? Well, سهلة. From, I don't know, 20 to 21 degrees Celsius برضه. Well, easy. مش 4,200 for 1 kilogram? يبقى times 10. 42,000 for 10 kilograms. Basically, just by plugging this number in, انت تقدر تعرف with the material needs how much energy. When it comes to usage of this equation, you have to, it's very simple. You just have 4 values and you have to plug in 3 of the values that have been given وتجيب انت التالتة. Let's take a look at a quick example عشان نفهم بس بنستخدم ال equation دي ازاي. So in this example, he says, an object has a mass of 2.5 kilograms and a specific heat capacity of, look, here's the number, underline our, specific heat capacity of 1,760, so 1,760 joules per kilogram Celsius. Calculate the heat energy needed to raise the temperature of the object from 25 to 50. طب ما ايه ده؟ طب ما هو كده مديني الماس ومديني specific heat capacity ومديني delta T, and he wants me to get the energy. Here we go. E equals mc delta T. I want the energy, so M is 2.5 times 1760 times open bracket بقى because it's change in temperature. So 50 minus 25 عشان عايز أعرف ال difference which is 25 فمش محتاجة إيه لف ودوران كتير. So if you open up the calculator 2.5 times 760 times 25 هيطلع لي 110,000 joules. 110,000 joules. Okay. Good. Great. So I hope you don't have any issues with that. Let's move on to the final equation. Oh yeah, before I finish this particular point, let me point something out. الماس هنا بالكيلوغرام والماس هنا بالكيلوغرام. Sometimes the questions try to trick you by changing one of them into grams. Please make sure that both of them have the same unit. يعني لو أنا كنت مديك 2.5 kilograms وده joules per gram Celsius, you must change the mass of the object to the same unit of the heat capacity, okay? فلو ده بالجرامز خلي ده بالجرامز، لو ده بالكيلوغرام يبقى ده بالكيلوغرام. In this example ما كانش دي مشكلة because they're already the same. Finally, specific latent heat. Heat capacity is great if you go back ثانية واحدة want to change the temperature, raise the temperature of an object by 1 degree Celsius. But remember in وقت melting, وقت boiling, يعني during melting and boiling, we said that the temperature, I'm just going back to that graph, the temperature stays constant. During melting and during boiling, temperature stays constant. So if you try to use E equals mc delta T to calculate the amount of heat energy you need to melt or boil something, it won't work. Then it won't work because the delta T will be 0. There is no change in temperature during melting and boiling. That's a big problem. So what's the solution? We come up with another equation because why not? And there's no limit to how many equations we can write in the world. Actually, there is. بس يلا. So what equation do we use? We say E equals ml, where E also represents energy. أنا عايز أحسب الانرجي اللي محتاجها عشان أسيح a piece of ice, for example. M is the mass of that piece of ice that you want to melt, and L is short for specific latent heat, and that's up there. So what is it that? Just like how specific heat capacity represents how much energy you need to heat an object up by 1 degree, specific heat capacity represents how much heat energy you need to change the state of 1 kilogram at a constant temperature. تاني, it's how much energy you need to change the state meaning melting or boiling, it doesn't matter, melting or boiling, to change the state of 1 kilogram of substance at a constant temperature, because during melting and boiling temperature stays constant. Using this is quite simple, and برضو هنplug in values في equation and nothing is problematic. But I need to point something out. We have two types of change in state عندنا في الدنيا. We have melting and we have boiling. Melting is the change in state from solid to liquid. Boiling is the change in state from liquid to gas. During melting, you are weakening the bonds. During boiling, you are breaking the bonds. تقول لي إيه الفرق يعني؟ أقول لك الفرق بسيط. You need a lot more energy when you want to break the bonds than you want to weaken them. So during boiling, it takes more time and more energy to break the bonds than it is during melting to weaken the bonds. فده معناها إن ال latent heat اللي عندنا دي actually ليها اتنين versions. One for melting, which we call the specific latent heat L يعني of fusion. والتانية للboiling هنقول the specific latent heat of vaporization. When I say fusion, I simply mean, melting. Vaporization is another term for boiling. They will both be used in the same equation, مش فارقة. But you need to be careful, because if in the question he's talking about melting, هتلاقيه جاب سيرة الفيوجن. If he's talking about boiling, he'll talk about vaporization. Now, it doesn't only have to be boiling. ممكن يبقى boiling, ممكن يبقى evaporation, ممكن بدل melting يبقى بيتكلم عن freezing. It doesn't really matter. But melting and freezing are denoted by fusion. Boiling, evaporation, condensation are denoted by vaporization. تعال بس نشوف الإيكويشن بنستخدمها ازاي. Because remember, the target is to calculate how much energy you need to melt or boil something. So in this example, it says a block of ice has a mass of 200 grams. The specific latent heat of fusion of ice is 334 joules per gram, as in how much energy you need per gram. Calculate the energy that you need. He wants the energy, and معايا ال M ومعايا ال L, and notice he said latent heat of fusion because he knows he's talking about melting. Sometimes questions would want to confuse you by giving you both fusion and vaporization numbers. بس هنشوف دي بعد كده واحنا بنحل. Calculate the energy needed to melt the ice block or the block of ice. Well, easy. هنقول E equals M L. Energy equals mass في specific latent heat of fusion. ال M بكام؟ ب 200. That's given. Times 334. You will notice أنا ما غيرتش أي units ولا حاجة because sure this is in grams but the mass is also in grams. They're the same mass. Okay, same unit of mass. 200 times 334, let me pull out my trusty calculator. So 200 times 334 gives me 66,800. And remember, since we're calculating energy, the answer is in joules. Very, very good. And with that, احنا كده خلصنا شرح Unit 2 أو مراجعة Unit 2 كلها. So I'll take one final look at the questions. There don't seem to be any questions right now, but I'll wait for a few more moments because there's a little bit of a delay. So anyway, with كده احنا خلصنا Unit 2 with thermal physics. I hope you enjoyed it, and I hope you found this particularly useful. Abdurrahman Leroy Jenkins, you got the reference. Cool. Anything on WhatsApp? Nothing in particular. Okay, great. Oh, a question. How can we differentiate when the material is transferring heat in terms of conduction? Differentiate between conduction, convection, and radiation. Well, here's the thing. If the substance is a solid, or if it's a solid in contact with a liquid, like things are in contact with each other, لامسين بعض, that would be heat transfer by conduction. If the heat is traveling through a liquid or through a gas, yeah, it has to be through that, it's mainly through convection. If the heat is just transferring through whatever it wants, whether it's a liquid or a gas or empty space, and it's being emitted from the surface وملهوش direction of motion معينة, because radiation is always emitted in all directions. Convection has to go up and down. So if it's in all directions, that's called radiation, or infrared waves. Okay, any more questions? Seems like nothing else. Okay, we'll end our session here. Nice, finally be done with thermal physics part 2. And let's not forget the sponsor of today's episode, Mr. U. بيقول اسمه، معرفش ليه بيقول اسمه، هنتعامل نديله طاقية المرة دي. He's really happy خلاص إنه خلص الترمال فيزيكس، ومسك الثرمومتر اللي كان في إيديه لما كان شغال في TBS وسابها ومشي عشان فتح الشركة بتاعته، وعايش حياته بقى دلوقتي يعني، عنده فيلا وعنده حاجات تانية كتير يعني، ياcht والكلام ده. So anyway, Mr. U says goodbye and so do I. Have a great day يا جماعة النهاردة، خدوا بالكم من نفسكم. Please stay home and stay safe for the rest of these 2 weeks, and I'll see you hopefully tomorrow إن شاء الله, and hopefully without the echoing الغريب اللي حصل المرة اللي فاتت. Thank you and have a great day. Goodbye.